Good morning. So today we are going to discuss about system on chip, which is from module 4 of EC308. So nowadays everybody is using smartphones and tablets, and there are huge requirement is there in smartphones and tablets in terms of applications and hardwares. For example, games, music, video, we need intense graphics and sound, powerful processing. For internet surfing, we need a good aspect ratio for a mobile device and Wi-Fi capability, 3G, 4G capabilities. GPS requires GPS chip and compass. Then camera and video cam, we need good image processing modules, DSP modules. Then mobile health monitoring, we require bioelectronic ICs. And general, we need power, antenna and power control device. So that means apart from microcontroller or processor, we need extra ICs to control all these applications. So how do we integrate all requirements? We need DSPs, we need microcontroller, we need DA, digital to analog converter, analog to digital converter, memory, RF and power control device, antennas, amplifiers, various modules. So the solution for integrating all these requirements is SoC. So that's where we need an SoC to integrate all devices. SoC means system on chip. All the components in a single chip, that is system on chip. Now, what is exactly system on chip? It is a complex IC that integrates the major functional elements into a single chip or chipset. It may contains programmable processor, on-chip memory, accelerating function hardware, both hardware and software, analog components, opto microelectronic mechanical systems. The benefits of SoC is it's reduce the overall system cost. So when we purchase a smartphone, we need more applications with less cost. So when we use SoC, basically this SoC will reduce the overall system cost with increased performance, less power consumption, and reduce the size. If you look at the normal computer, desktop computer, it requires a bigger architecture, so that's why it need more power, so that's why it produce more heat, so that's why we are using cooling fans and all. But for smartphones, we need an optimized system, optimized software, reduce size with low power consumption. So for meeting all these requirements, we are using SoCs. SoC is not only chip but more on system. SoC is equal to chip plus software plus integration. So that is actually SoC is a combination of chip software integration. So SoC chips includes processor, ASIC logics, analog circuits, embedded memory, OS, compiler, simulator, firmware, driver, protocol, various development environment, etc. SoC integration includes the whole system solution, manufacturer consultant, and technical support. So before SoC, there is a graph. The red color shows the technology utilization. The blue color is the technological requirement or complexity of our need. So there was a huge gap in between technology utilization and requirement. To meet this gap, SoC is a solution. So one solution to the design complexity productivity gap is to make ASIC design more standardized by reusing the segment of previously manufactured chip. These segments are known as blocks, macros, cores, or cells. The blocks can either be developed in-house or licensed from an IP company. IP means intellectual property. Cores are the basic building blocks. So to understand that, so this is an image of Snapdragon process, SoC. So basically, many mobile companies, if you just go through the details or specifications of the devices, you can find the name Snapdragon. The Qualcomm is the company which is making the Snapdragon platform. So it's an SoC example. Here you can find a Cortex processor IC. So this IP is created by, so here we can see IPs. The blocks are either developed in-house or licensed from an IP company. So Qualcomm is not actually creating the IP for the processor. The processor IP is from ARM. And some companies like, sorry, if you buy a mobile phone of Redmi or any other mobile phone with a Snapdragon processor, that Snapdragon processor is having IP which is created by ARM company, and the mobile company that is manufacturing the processor basically using that IP. But in the case of some companies like Samsung, they have their own in-house intellectual property processor. So that is another thing. So here we are in Snapdragon, we are using an IP from ARM, and the company Qualcomm, Qualcomm is bought that intellectual property from ARM to manufacture the Snapdragon. So apart from the processor architecture, we have DSP for image and audio processing and all, memory, display processing, modem, USB, ISP modules, multimedia module. So it's a combination of many chips. So that is why this is known as a system on chip. So it is integrating all kinds of chips to a single module. So before SoC, we have printed circuit boards where we will make the provision for each package to place. So where we will place keep the packages. So when we use these kinds of hardware, PCB hardware, it will create a lot of application problems, then work functional problems, then interconnection delays and all. So instead of making like this, we are using a SoC. We don't have a separate parts. Every part's inside a single chip. So for example, this is an FPGA chip. So this SoC will looks like only a single chip rather than separate chips. So these are the comparison of various technologies: chips on board, system in package, system on chip. Chip on board means mounting IC chips directly to the PCB. So this is that example. Here we have a PCB and we are mounting the IC chips above this PCB. The basic method of improvement within the technology paradigm is substituting different materials to reducing the interconnect delays. System in package, stacked chips or packages for reduced form factor, improving performance and power efficiency by short direct connection channel. This is another technology. And our technology is system on chip. This is a complementary system on chip, reducing the form factor, power consumption, heat dissipation, analog mixed signal integration. So this is the performance comparison. This is COB, this is SIP, this is SoC. W for worst, M for medium, B for best. In the case of performance, SoC is the best. In case of form factor, SoC is the best. In case of signal process packing density, in that case also SoC is the best one. And when it comes to the cost also, SoC is cheap compared to SIP and COB. Heat dissipation. Heat dissipation is best in COB boards compared to SoC, but SoC is having medium in that case also. Then functionality is best in SoC. So overall, if you compare all these technology, SoC is the best in the market. So that is why each product or each company, every company is selecting SoC technologies to manufacture the product. So based on the comparison, SoC possess more potential. So these are various performance graph of various SoCs. Qualcomm Snapdragon. This one we mentioned earlier, the block diagram of Qualcomm. Then we have NVIDIA Tegra SoC, Samsung in-house SoCs, Exynos. So the Chinese mobile companies like Redmi and all, they are purchasing Snapdragon SoC from Qualcomm. But Samsung is having an in-house SoC that is known as Exynos. So it is manufactured in Samsung fabrication lab. So this is the SoC of Snapdragon SoC, Texas Instrument SoC, Samsung SoC, NVIDIA SoC. So all these SoCs upgrading every year to obey the Moore's law concepts and all. When we design and implement SoC, we have different challenges. Like we need to reduce the transistor size to increase the transistor density. Then we need to reduce the process size. We need to increase the performance. Power issue we need to increase. We need to improve the power optimization to reduce the power issues and all. Then we need to reduce the cost. We need to reduce the signal complexity. But when you implement all these things, SoC, what happens is that when we scale up the devices architecture and SoC architecture, we need to face a lot of power issue. We need to face a lot of cost issue. We need to face a lot of performance requirement and all. So the complexity will increase when we implement a bigger SoC system. So we need to improve the technology and the various technological aspects to make SoC implementation as a simpler one. So this is a graph where when we increase the system complexity compared to SiP, SoC is having higher cost. So that is a challenge. We need to make it to a linear one rather than an exponential one. In a SoC in market, when you go through the market of SoC and all, ARM is most dominant in smartphone processor, like Snapdragon IP. Snapdragon uses Cortex-A architecture. So like that, many companies are manufacturing processor with ARM IP. So ARM is basically sharing 95% of the market share of SoCs. So the benefits of using SoC. There are several benefits in integrating a large digital system into a single integrated unit. This includes low cost per gate, lower power consumption, faster circuit operation, more reliable implementation, smaller physical size, greater design security, can be cheaper when using ready-to-go components. The drawbacks. The principal drawbacks of SoC design are associated with design pressures imposed on today's engineers, such as time to market demands, exponential fabrication cost, increased system complexity, increased verification requirement. So depends on the market need. We need to increase the architectural complexity, increase the performance and all. So in that case, the designer or engineer have a high pressure to increase the system or increase the performance. For when we increase the performance, we need better and complex architecture that will increase the fabrication cost and complexity. So these are the drawbacks that there is no end or limit for the market needs. So to flow with the market or to move with the market, the engineers have huge pressure. And major applications of SoCs: speech signal processing, image and video signal processing, information technologies, data communication. So these are the various applications. A lot of applications for SoC. So technological advances means that complete system can now be implemented on a single chip. Earlier we have separate chips for separate applications and all, and we are mounting all these technology chips to a single board. Now instead of a board, we are placing all the application system to a single chip. So that is a technological advancement. The benefits that brings are significant in terms of speed, area, and power. So when we place everything into a single chip, that will reduce the area, increase the power dissipation, decrease the power dissipation, and increase the speed of operation. The drawbacks are that these systems are extremely complex, recurring amounts of extremely complex recurring amounts of verifications. So hence the system is more complex. We need a complex validation system, complex verification system and all. So that is the drawback of this SoC. The solution is to design and verify reusable IP. Okay, so before going to the next slide, we will watch a video.
Hey friends, welcome to the YouTube channel all about electronics, and in this video we will see what is system on chip. So today we are living in the era of a smartphone and a tablet, and in the past decade the technology has been evolved so much that using this smartphone and tablet we can do almost all the stuff that we were used to do with a desktop and a laptop. So using this smartphone and tablet we can do a stuff like gaming, web browsing, photo editing, creating documents, media streaming and many more things. And yet these devices are quite compact compared to the desktop and a laptop. And yet they contains almost all the parts which you see inside the desktop and a laptop. So almost all the components that you see inside the motherboard of any laptop or a desktop are integrated inside a single chip in the smartphone. So the entire system which is required to run a smartphone is integrated inside a single chip, and that is known as a SoC or a system on chip. And thanks to the leading manufacturers like Qualcomm, Samsung, Apple and MediaTek, it is possible to integrate all the components inside a single chip. And sometimes if you see the size of this system on chip, they are as small as size of a coin. So now the question is, how is it possible to integrate all the parts inside a single chip? So there are many reasons behind that. So let's find out these reasons. The first reason is the processors which you see inside the smartphone are not as powerful as processors which you find inside the desktop and the laptop. So don't get me wrong that the processors which you see inside smartphone are powerful enough, but if you compare them with the processors of desktop and laptop, the processors in desktop and laptop are quite powerful. So if you have seen any motherboard of any laptop or a desktop, you must have observed that the processor is enclosed by the heatsink and the cooling fan, because these powerful processors generates a lots of amount of heat and they need some sort of cooling. So just imagine the size of your smartphone if the same processor with all the cooling arrangement is fit into your smartphone. And forget about the cooling. If you put this processor inside your smartphone, then your battery of the smartphone would be died in just half an hour, because these processors are quite power hungry and requires a lot of amount of power. So the fact is that the processors which you see inside a smartphone and tablet are designed using a different architecture. So the most of the processors which you see inside a smartphone and tablet are designed using the ARM architecture. And the system on chips which is designed using this ARM architecture are quite powerful as well as the power efficient. One more thing is that the operating system which is designed for this smartphone is optimized for this system on chips. So although on paper this smartphone processor doesn't look powerful compared to the desktop processors, but because of this software optimization, you hardly feel any lag when you are operating this smartphone and tablets. Apart from that, the advancement in the manufacturing technology has allowed us to integrate more and more transistors inside a same area. So not only in the smartphone but in desktop and laptop also, you will see that many parts are integrated inside a same chip. So these are some of the reasons why we are able to integrate all the components inside a single chip. So now as we know about what is system on chip, now let's find out what is inside this system on chip. So the first thing that you find inside the system on chip is the processor, and we have talked so much about this processor. So the next thing that you will see inside the SoC is the GPU, which is known as a graphical processing unit, and it is responsible for all the graphics related activity inside your smartphone or a tablet. The next thing that you will see inside the system on chip is the DSP, which is known as a digital signal processor, and it is responsible for the activities related to audio processing, video processing and somewhat related to display. So in some system on chips you will find this audio and video processing module as a different module, while in some cases they are integrated inside a same module. The next thing that you will see inside the system on chip is the memory element, which contains the storage memory, that is a read-only memory, and the volatile memory, that is a random access memory. So now the next module that you will see inside the system on chip is the connectivity module. And this module ensures that the user have all kinds of connectivity like Wi-Fi, FM radio, USB, Bluetooth, sometimes GPS and cellular radios. So these are the basic modules that you will see inside the system on chip. Apart from this, some higher-end system on chips also contain some other modules like a module for the camera, location, security and the sensors. Now sometimes due to the size constraint, it is not possible to integrate the random access memory or a RAM inside this system on chip. So in such scenarios, this memory package is stacked above this system on chip package and they are connected using this ball grid array. So this kind of packaging arrangement is known as a package on package arrangement. And this type of package on package arrangement reduces the cost as well as the size. Now in scenarios where the memory is outside the system on chip, you need to establish the connection between the CPU and the memory, and that is done by the module known as a North Bridge. So this module ensures the connectivity between the RAM and the CPU. So these are the modules you will find inside the today's system on chip. So far this system on chip technology is more or less limited to the smartphone and the tablets. But in the near future, you will see this system on chips in almost all the devices and in all the applications. So now the question is, what about the desktop and the laptop processors? So the answer is they will be still used in the applications where the size and the power consumption is not an issue. And
So can anyone say what is this architecture? In this architecture we have I2C, CAN, UART, Ethernet, SPI, PWM, IR, temperature sensor, digital to analog to digital converter, touch sensor, memory, Wi-Fi, Mac, radio. So everything is available in this system. So this is an SoC, and this SoC we are commonly using in our hobby projects and all. So this is the device, ESP32. So it's a very simple device, but when you look to this chip, it will look very small, and we will think that we don't have enough applications in this device. But when you look to the architecture, we can find that it's a very big system. It's having a lot of capability in doing projects and all. Even it's having a cryptographic accelerator, RSA algorithm. Every algorithm, everything is available in this system, and real-time clock also available for power management and all. So we can try in your home by doing small projects using this system on chip ESP32, and it is Arduino compatible. You can use Arduino IDE for doing projects and all, and even you can try in your home about inter-process communication and task synchronization process. I will show you one video example of inter-process communication and task synchronization using ESP32.
Hello everyone, in this 2-minute tidbit we'll take a look at using both cores of your ESP32 using the Arduino IDE. All Arduinos can do a type of multitasking. As you can see here, the LEDs are blinking at a different rate. This is using a technique described in the blink without delay example, where you use millis to decide if a task is due to run. This works out fine because, like most things you do on the Arduino, the digital write happens so fast that it doesn't impact the timing loop at all. If we upload the same sketch to the ESP8266, it works as expected. But now if we change the sketch, so instead of blinking the red LED we make a network call instead, the green LED does not work properly at all anymore. This is because of how long network calls take, especially secure ones. So as you can see, the device is still in the middle of the network call task when it should be toggling the LED. If we upload the same sketch to the ESP32 we see the same behavior, but unlike the other Arduinos we can do something about it. Andreas Spice has a really good video about this same topic where he goes into details about how the ESP32 has 2 fast cores but the Arduino IDE only uses one of them. I'm going to go through one of the examples that Andreas provides in his video, but I definitely recommend checking his video out, it's really good. To convert the example over to one that uses both cores is actually pretty straightforward. First you need to define a task handle, I've called mine task 1. Next you need to create a function that's going to run on the second core. The function needs to have a void star parameter like this, and also needs to have an endless loop inside it. And finally, in the setup, we call xtask create pin to core. Andreas's video goes through all the different parameters here, but the important one for us is the task function, the task handle, and then that we want it to run on core 0. You can now remove any code for blinking the green LED from the loop. And now the LED blinks perfectly every half a second. That's because it's core 0 that's looking after blinking the LED, while core 1 is busy making the network call. To give a more practical example of how this is useful, one of these LED matrix displays every time the text moves is a task on the Arduino. So for this social media stats counter I built using an ESP8266, I got around this issue by stopping the text on the screen when there was a value displayed. This gave me a chance to make a background call to fetch new data. But by making use of both cores of the ESP32, using one to drive the display and the other to make the network calls, we can continuously scroll the text even when we're fetching that data from the internet.
So ESP32 is very cheap SoC. You can buy it from your nearby electronics shop. You can try the practical examples. So whatever you learned in embedded system about SoC, inter-process communication, all these concepts you can apply into this SoC with the help of Arduino IDE. So Arduino IDE is also, it's an open source, so you don't need to have any license or any amount to install that software. So try to implement any kind of task synchronization and all, and to try to create a video with ESP32. So these are the references. So basically we can go through the Qualcomm Snapdragon details, then ARM architecture. Thank you.